All right, so I'm going to kick this off in a few minutes, but I just want to put this up to remind everybody that this is where we left off last time, and this is where we're going to pick up today. We're trying to propose a synthesis pathway that would take us from A to B on some of these more complicated aromatic substitution reactions. All right, so let's do this first one. This is sort of where we left off last time. All right, and what we need to do is we need to look at our product and we need to think of how we know how to put each one of these substituents on that ring. Okay, so for bromine, that would be that bromination reaction, Br2 and aluminum bromide or iron bromide. All right, now, I have a feeling that a lot of us were tempted to look at this alkyl group right here and say, a Friedel-Crafts alkylation reaction, all right? There's two big problems with that. So first of all, if we do an alkylation reaction with what would be 1-chlorobutane, all right, we got two major problems here. Number one, a bromine is what? An orthopara or a meta-director? Orthopara. And an alkyl group is a what? Orthopara or meta-director? Orthopara. And yet in this molecule here, these two functional groups are sitting what? Ortho, meta, or para to one another? Meta. All right, so crap. First of all, we got a problem because I can't possibly make these starting out with those two reactions. I can't possibly make my meta product with these two orthopara reactions, all right? But we have another problem here. Let's take a benzene ring and let's actually perform that proposed Friedel-Crafts alkylation reaction. Right? I am not going to get butylbenzene as my major product. All right? This is not what is going to be our major product in this reaction. All right? Why not? Hydride shift, all right? So remember these Friedel-Crafts reactions with all of our electrophilic aromatic substitution reactions. We took a look at those electrophilic species. Well, for this reaction here, when that aluminum chloride steals that chlorine away, it's going to create what is our intermediate in our, our electrophilic species in these Friedel-Crafts reactions, a carbocation, right? And that primary carbocation is not going to just chill there as a primary carbocation. You're going to have a hydride shift and form a secondary carbocation. And that will be the electrophilic site, the electrophilic carbon in this reaction here. Okay? So you will get carbocation rearrangements, and your major product will actually be like this sec-butylbenzene thing. All right, so not only would that strategy not work from just a synthesis strategy standpoint, it's also not going to work because of these hydride shifts, right? So don't forget about those with regard to our alkylation reactions. Anytime we have that carbocation intermediate, we got that little asterisk in our brain that's like, watch out for hydride and methyl shifts. All right, so instead, how are we going to put, I'm going to be lazy and copy and paste. How are we going to put this butyl group onto that benzene ring? All right, this is when we were actually first introduced to this reaction of reducing those ketone groups, those Friedel-Crafts acylation products. So what I'm first going to have to do is an acylation. And then I can reduce that with the zinc HCl heat method. What's up?
Wouldn't you want to do the VR first because it's going to be meta?
Oh, no. So I'm real quick. We'll talk about the order of reactions later. I'm just making sure that we can see the real way that we have to put that butyl group on there. Like looking at this reaction divorced of that previous problem. Okay, cool. So this is our strategy. We're going to have these two reactions that we're going to have to do in order to put that butyl group on there. All right, so let's go back here and take stock of this. Okay, we're saying it's not this one. Instead, we got these two reactions that we can do. Our Friedel-Crafts acylation reaction, and then we're going to use that zinc, HCl, and heat method. All right, but absolutely, now we got to think about the order of these reactions here, the order in which we're going to perform these reactions. All right, and so again, we want to sort of assign, if we do this first reaction and we put this acyl group on, would that be an orthopara or a meta-director? That would be a meta-director. And then if we follow through with this second reaction here, that's going to convert that meta-director into an orthopara-director. So which one of these do I want to do first? Well, because in my product these two groups are sitting meta, I need to first put on that meta-directing group. All right, and now importantly, I cannot follow that up with that reduction reaction right away because that will convert my meta-director into an orthopara. So absolutely, the second thing I'm going to have to do is that bromination reaction. That'll put that bromine in that correct position on the ring. And then to get my final product, I'll use that zinc HCl heat method. Right? So absolutely, the order in which we perform these reactions is super important. All right, so we got another one here. All All right, let's sort of lay out our reactions that we can do here. This amine group, importantly, we don't sort of have any way to just put that on in one step. All right, what we can do is this is another one of those special 4 that we made note of, where first we put on a nitro group, and then we reduce it. That's that other one that's pretty similar but not the exact same. Think HCl and NaOH, right? Yeah. Our bromine, we got our good old-fashioned bromination reaction. Okay, and then for our toluene, we can use that Friedel-Crafts alkylation reaction. All right, so given these 4 reactions here, all right, I will tell you that we are going to use these 4 reactions, and I want you to come up with the order in which these 4 reactions need to be used to create that product. All right, so I actually see 2 different ways that we could do this here. I'm going to copy and paste this thing down here so we can keep in mind kind of what we're looking at. All right, but then I'm going to kind of annotate as we go on our product side here. Okay, so the first thing that we could do is to do that Friedel-Crafts alkylation reaction. That would put that methyl group on there and create toluene. All right, so then my next substituent would be directed to either the ortho or the para position. Well, looking at my product here, I want a nitro group on that para position. Okay. But now if I look at what reaction I need to do next, importantly, if I did this bromination reaction, the nitro group is the stronger of the 2 directors, and that would stick the bromine down here. So I don't want to do that next. I'm going to first reduce that nitro group. I guess this is 3 and 4. To NH2. And now these are both ortho-para-directors, but importantly, that nitrogen amine is the stronger of the two. So it's going to get its way in terms of where that incoming substituent is going to go. And so now I can do my last reaction here, my last step. Let's call it a step. There we go. I can say this is step 3. This is step 4. Okay. And that will put that bromine in the correct position. All right. There's actually another perfectly equivalent way that we could have done this. So just to kind of show both, just so you can check depending on which one you had. You could have actually first started out with your other ortho-para-directing reaction. Okay, that'll put that bromine on. And now my next substituent is going to be directed to those ortho-para positions relative to the bromine. All right, so then we can do our nitro reaction, because one of my products will put that in that ortho position. Okay. Again, at this point, I don't want to do my bromination reaction yet, because that nitro group is going to direct any incoming substituents to a position that's meta to it. But if I next do that zinc acid followed up with base trick, now that converts it into a stronger ortho-para director. Boom. So both of these would be full credit answers here. What's up?
Can we put nitro group first as another alternative?
Nitro group,
As the
and then
first
you reduce it. Yeah, you could actually do, yeah, there's a third one. Yeah, good call. As long as I, so another one, boom. Then I can reduce it. Then you can do either one of these next. Cool, so, bunch of different ways to do it, all right? Bottom line is, though, we do have to pay attention to the order in which we do our reactions, all right? Oftentimes, there is more than one way to get from A to B, and that's perfectly equivalent. There's actually another way that we could do it if we used instead our Friedel-Crafts acylation and then reduction technique. I don't know why we would want to do it in 5 steps instead of 4, but we could do it if we wanted to, right? Another perfectly equivalent way to do it. All right, so much fun. All right, cool. So, last thing that we want to review real quick with regard to this chapter is, again, we talked about following these reactions. So take a second and follow this reaction here. All right. All right, that first reaction. We'll put a chloro group on there. That chloro group is going to direct the next incoming substituent to the ortho or the para position. So we're going to get a mixture of both.
Wouldn't it be an alpha group?
Oh, yes, but that's not the reaction I meant. I apologize. Trying to go in a specific place here. My bad, y'all. So yes, it was, and if that's what you put, fantastic. And that is, then the third step would make no sense. So I apologize. Cool. All right. So now we have this nitrochlorobenzene here in the ortho in the para position. And then we have this third step with sodium hydroxide. All right. What the heck is the sodium hydroxide doing for us here? So first of all, when you see a molecule like sodium hydroxide, when you see any oxygen with a negative charge, I hope the very first thing you think of is base, right? That is what we use those for so very often in the lab, okay? So yes, base, fantastic. When I look at these molecules here though, I have no donatable protons, right? There's no acid in these molecules. So sodium hydroxide is a base. Number one thing you should think of in your mind. But sodium hydroxide is also a nucleophile, okay? And so remember, this was this last class of aromatic substitution reactions that we learned about was those nucleophilic aromatic substitution reactions. And there are a lot of qualifications that a molecule had to meet before it was able to undergo those. But those two qualifications were strong electron withdrawing group, check, check, and good leaving group in the ortho-para position, check, check, right? So what we're going to have here in this third reaction is a nucleophilic aromatic substitution reaction where that leaving group is being substituted for that nucleophile, in this case that hydroxide ion. All right, so bottom line here is we sort of talked about those 5 electrophilic aromatic substitution reactions. We kind of beat that topic to death, right? But then we also talked about this additional aromatic substitution reaction, the nucleophilic one, NAS. And don't forget that that exists because it kind of plugs into our synthesis strategies. All right, so then I want you to do one more for me here. Get me from A to B on this one. so if we're going to go through here and sort of try to figure out what reactions we can do to generate these groups, for our chlorine, we have that chlorination reaction. All right. For our amine group here, we could do our nitration and then reduce. Okay, but for this OH group here, the only way that we can put an OH group on that ring is with a nucleophilic aromatic substitution reaction. All right, I will say this, we could also put an amine group on this ring using a nucleophilic aromatic substitution reaction and sodium amide. And maybe from a pencil and paper standpoint, that's all well and good, but from a practical standpoint, that would be a ridiculous way to do that, all right? You're gonna bypass using what are very cheap and very accessible reagents to use one of the more expensive and extremely difficult to handle sodium amide. No, probably not, right? So practically speaking, we don't really handle sodium amide very much at all. It is a incredibly strong base, highly reactive. So pencil and paper wise, we'll see it quite a bit, but yes, it is a bitch to work with. So practically speaking, you will not really see it out in the wild very much, all right? Cool, so these are our these are our reactions that we're gonna mix and match here, okay? Now, importantly, for that nucleophilic aromatic substitution reaction, I have to have a strong electron withdrawing group. Well, cool, the nitration reaction satisfies that requirement. Check, check. I got one, but I don't have my other requirement, which is that good leaving group, okay? I do have a good leaving group on there, chlorine though. Everybody's like, well, wait a minute, chlorine's on there. But remember, there was a big caveat to that good leaving group in terms of the position that it has to be in relative to that electron withdrawing group, which is the ortho or the para position. That chloro group in that meta position is not substitutable, all right? So we're gonna have to do another, either chlorination or bromination reaction, doesn't matter, in order to put the leaving group in that particular position, in the correct position here. All right, in fact, that's what we got to do first. Okay, so again, I'll kind of make a copy of our target and then annotate as we're going here. So if we first put that chlorine on our ring, all right, what you're going to find in your nucleophilic aromatic substitution reactions is you have to put the leaving group on first so that it can direct the nitro group, direct that strong electron withdrawing group to the correct position. All right, I guess we can use the excess NBS method as well. Cool, so then the second reaction I'm going to do is to put that nitro group on there, right? That'll put it in the correct position here. Okay? These next two steps could have been done in any order. We're going to both substitute out that leaving group for that hydroxyl group. So we need to add in our nucleophile. Okay, and we're going to add that additional chloro group. Again, those two steps could have been done in any order, but importantly, they have to be done before this last step because you're relying on that nitro group's strong meta direction to get that to the proper position. All right, and then the last step here would be to reduce that nitro group to our amine, our zinc HCl sodium hydroxide? All right, and that gets us from point A to point B. What's up?
Could you also do it where you start off with the HNO3, H2SO4 to then get the chlorine to the meta position first and then add in?
Yeah, the problem is that you would never be able to get anything to this position then with that nitro group on there, because it's going to direct everything to that meta position, right? And if you then reduce it to aniline, all of a sudden you don't have your strong electron withdrawing group to do your nucleophilic aromatic substitution. Okay, so, all right, cool. So that sort of closes out the review portion of what we did this chapter. Let's talk about the exam for a little bit. Your exam is Monday and Tuesday of next week, okay? In terms of studying for your exam, so first of all, you can see with these problems here that having like a good understanding of these reactions that we learned is really important, right? I gotta look at this and have reactions come to mind that I'm going to use, okay? Now, importantly, for all your problems on your exam, I don't expect you to have these reagents memorized, all right? There will either be a bank of reagents that you pull from or some sort of selection like that, right? So it's not about memorizing these, but you need to be able to spy them and know what they do, okay? So I don't care if you remember the zinc HCl NaOH order, but you need to see that combination and know, aha, I know what these do, okay? So first of all, then how best to study for your exam? A really great thing to do is to make flashcards of these reagents, okay? Have some sort of a list where, again, because you need to spot recognize it, right? So some list, some summary, all right? So how do you go about doing this? All right, let's remind ourselves here. We do have a textbook, and our textbook is super helpful sometimes, all right? In particular, one of the very useful parts of our textbook, let me see if I can get a good example, is at the very end of a chapter. Well, all over we got these little summaries here, but let's see. At the very end of our chapters is like a little summary page. Cool, all right. Is like a summary page where it lists all these different reactions that you studied in that particular chapter, right? So this is a great place to turn to mine for all the various reactions that we studied to make a list of. Obviously you have them all in your notes, but they're kind of dispersed and all that stuff. To be clear, this is from an older chapter. It's just the first thing I grabbed in my huge list of pages here, all right? But anyway, you want to turn to our chapters, turn to the end where there's that nice summary of reactions that were covered in that chapter, okay? Because again, spying those reagents are going to be very important. I don't really have any expectation that you have them memorized, but again, you need to know what they do, all right? Cool, so then format for the exam in terms of what to expect here. So what you can kind of expect is a mixture of these multiplication as well as short answer questions, right? So you're going to go through, you're going to have a Scantron. The Scantron will be provided for you. All right, there's going to be some questions that are multiple choice format. So for each one, you'll go in and bubble on your Scantron. And then you'll get to these questions that are specifically labeled short answer. And that is where you're just going to draw your actual product. Or in this case, we're going to draw a house. All right, in our short answer box. All right, those will be graded by me, right? I'll get your exam booklets, and that's how those questions will be graded. Okay? Because these are kind of intermixed within the exam, what you'll find is that your Scantron questions are numbered, your multiple choice questions are numbered so that they correspond with your Scantron bubble. And then when you get to these short answer questions, they're lettered, all right? And the whole point there is that it just doesn't interrupt the numbering scheme of the questions on the Scantron. Cool? Check out? Awesome, all right. So in this remaining time, just to sort of rewind back, and specifically I want to rewind back to when I wasn't here. and make sure that we're on the same page about what should have been covered during when the substitute was here. All right. On Monday, we will have our exam 1 review session where I'm just going to rewind back to the beginning and sort of just pick as many practice problems as I can do in that period. That is the first day of our exam, so I won't take attendance on it. There won't be a daily quiz on that day. And if you need to use that period to take your exam, you can, right? So bottom line is if you can squeeze lecture in, there will be like a brief review period that you can go over. I mean, we can't go over a ton in 50 minutes, but we're gonna just kind of rewind and try to do as much as we can in that period, all right? But cool. So again, first thing to review, all right, there were 2 sort of things covered on that day. All right, so first would have been determining aromaticity in compounds that are heterocyclic compounds, right? They have another atom in there other than carbon, and importantly, this atom has a lone pair on it, all right? So an example would be this thing here, furon, tetrahydrofuron, no. Yeah, whatever. It's got a funky name. Okay? And we need to look at this compound here and determine whether this compound is anti-aromatic, aromatic, or non-aromatic, right? Our classification of aromaticity. All right? So we had those 2 rules for being aromatic. 1, you had to be a conjugated ring. And 2, you needed that odd number of electron pairs. Those were our 2 qualifications. All right? So what we're going to do is we're going to first see if this meets rule 1. 1, 2, 3, 4. All those carbons are conjugated here. Right? But then I get to this oxygen. And the question is this a fully conjugated ring? Is this oxygen going to be participating in this network of conjugation here? All right? And what makes this unique is that there isn't a pi bond pair of electrons here, but rather there's these lone pairs, all right? And the important thing to remember about our lone pairs is that lone pairs get to choose. All right? This molecule, this atom, this oxygen atom, it gets to choose whether or not it's going to participate in this ring conjugation. It gets to choose what type of orbital it puts that lone pair into, all right? If it puts that lone pair in an sp3 hybridized orbital, that'll break that conjugation of the ring, so it'll fail rule 1 and be non-aromatic. Or it can put that pair of electrons into a p orbital. It can be sp2 hybridized. And then that pair of electrons gets to play with the other electrons that are in that ring, right? It gets to be conjugated, all right? So lone pairs get to choose, and they'll only say yes if it will make the compound aromatic. All right, so before I can even answer rule 1 here, I got to move on to rule 2 and see if this pair of electrons join the party, whether or not that would make that compound aromatic, right? And again, not only do I have to have a fully conjugated ring, I got to have that odd number of electron pairs. So I'm going to count my number of electron pairs here. 1, 2, and if that lone pair joins, that will make 3. So is that lone pair going to join the ring or not? Yes, all right, cool. So this particular compound here would be aromatic. Right, and in particular, that oxygen will arrange itself to be sp2 hybridized. Okay, So now that pair of electrons, that lone pair that I've highlighted in red, we would consider to be delocalized. It is now spreading itself out, traveling in a circle around that ring like all the other electrons are, all the other pi electrons are, right? It is now a delocalized electron pair. What's up?
So are we just going to include the other lone pair on there?
No, good question. So what's going on with the other lone pair here? All right. The other lone pair we would call localized, meaning it is not participating in that ring's conjugation. It is just sitting, chilling on that oxygen atom, not talking with any of the other electrons in the molecule. This one would be what we would call localized. Okay? And importantly, even though oxygen's got those two lone pairs, it can never delocalize both pairs at the same time. It is always going to have at least one pair of electrons be localized, all right? And that just has to do with the geometry of those orbitals. Those peanut-shaped p orbitals, you can only have one that's pointing in the right direction of that ring, right? They all got to be pointed up in that same direction for them to be localized. You're only going to have one orbital that can do that, okay? Cool, so the other one we would call localized. Okay, cool. So then the last thing, and it's pretty deceptively straightforward, all right, but let's make sure we have that. What we call molecular orbital diagrams of aromatic compounds. All right, and what we're going to do is two examples here. Good old quality benzene and our cyclobutadiene. Holy hell, that was awful. All right, and before we even get started here, what do we know? I hope we kind of just know these at this point. Benzene is what? Aromatic, anti-aromatic, non-aromatic? All right, fantastic. And what about our cyclobutadiene here? That one's anti-aromatic. All right, and what we're going to do is we're going to build these molecular orbital diagrams, and they're going to help illustrate why aromatic compounds are so stable and why anti-aromatic compounds are so unstable. Okay? Now, before we get started here, molecular orbital theory, where does that come from? Right? This is not something that somebody sat down one day and was like, yeah, this makes plenty of sense. Perfect. Let's spitball this kind of thing. No. This crap falls out of the math. This is very complicated quantum mechanics. This whole theory is really just a giant math problem. And it is math that is well beyond the scope of this particular class. So we're not going to do any math. What we're going to do is we're going to build this cute little diagram, and that's going to help explain something, a phenomena about this aromaticity. But importantly, where did that cute little diagram come from? It is just a simplification of these principles that were laid out in the math, all right? Cool, so what we're going to do is we're going to build these diagrams where we have energy on our y-axis. I'll make two of them here. Okay? And sort of the important principle here that we're going to use is that our atomic orbitals mix to form what are called molecular orbitals. All right, so if you remember back to general chemistry, you were talking about S's and P's and D's, right? And that was if you had just an individual atom all by itself, where does its electrons live? Okay? When you start putting atoms together, those orbitals mix together to form your covalent bonds. And so what happens is the atomic orbitals that you start out with mix together to form what are called molecular orbitals. So these are where the electrons are going to live in our molecule. These represent our covalent bonds, all right? And importantly, the number of atomic orbitals we mix together will create that same number of molecular orbitals. Okay, cool. So the way that we draw these cute little diagrams here is we're going to take the shape of our aromatic compounds and we're going to orient it such that one of the points is pointed down. All right? So for my cyclobutadiene here, I can't use it as the square. I'm going to have to rotate it so it looks like a diamond here. One of our points have to be facing down. So let's just note, point down. All right? And now at each one of these intersections, each one of these corners, I am going to put an energy level. Now, how many electrons are we going to fill into this diagram here? Well, we need to look at how many electrons are delocalized in this molecule here. All right? So we have these odd number of electron pairs. Each pair contains how many electrons? 2. Cool. So what we're going to do is we're going to fill this diagram in with these 6 electrons. All right? Now, you learned these filling rules back in general chemistry. Importantly, you always fill from the lower energy to the higher energy, right? So we're always going to fill from bottom to top here. All right, so that means I'm going to start out 1, 2. Whenever we fill our orbitals, we'll have 1 spin up and 1 spin down electron. All right, Pauli exclusion principle. I don't remember who the other guy is. Aufbau principle? Sure. And then we got Hund's rule, which is our third rule for filling in these diagrams, which says that if we have two orbitals at equal energy, right? So notice how these two here are going to be the same energy level. They're the same energy on my graph. We have to half fill first, and then we'll go back and double up. So when I put in these electrons, I'm going to go 1, 2, 3, 4. All right? So everybody take a minute and see if you can't fill in our cyclobutadiene correctly here. How many electrons am I going to put in this diagram? 4. So I'm going to start at the bottom, 1, 2. But then I get to these 2 that are equal level. So I'm going to go 3, 4. All right. So this diagram right here helps to explain why aromatic is good and anti-aromatic is bad. All right. Over here on the left-hand side, we have a bunch of paired happy electrons. They're sitting in those low energy orbitals. They're all sort of paired together and happy. Okay? Over here on our anti-aromatic compounds, we have a bunch of unpaired electrons. All right? And these unpaired electrons are mad. All right? So why is that? Kind of sort of relates back to physics here, and again, we're not going to do any math, but 2 important things, 2 important facts kind of combine to make these electrons mad, all right? The first is that unpaired electrons are paramagnetic, which means that they interact with a magnetic field. Okay, oh shit, sorry. And the other thing is that electrons that are moving in a circle as they are in a conjugated ring like this, they are generating a magnetic field. So these electrons are being hit with this magnetic field that they're generating, which is destabilizing this molecule. All right, it's electrons in circle, magnetic field. Okay, charges moving in a circle, generating magnetism is a property that you would learn about in a physics class, probably a pretty advanced one. I think you need some vector math in order to do it, all right? But yes, charges that move in a circle, they generate magnetic fields. And then electrons that are unpaired interacting with magnetic fields is, again, a very mathy kind of quantum principle, all right? But anyway, these two factors combined make these electrons very mad, and thus are anti-aromatic compounds bad. Wonderful. All right, enjoy your weekend. Good luck on studying for your exam.